Okay, welcome. Thanks for coming in on a late afternoon. And my name is Brad Calder, and I'll be giving a talk on what's new with Windows Azure Storage, as well as going over some of the internals for Azure Storage. Clapping already, all right. Okay, so for the agenda today, I'll start off by talking about where we are with storage in the cloud today. Then I'll talk about what's new in terms of some minor features we have now for blobs, tables, and queues. I'll then focus on something we released last month called Storage Analytics, talk about geo-replication, which was just announced today, and then spend the rest of the talk focused on Windows Azure Storage internals. So where we are with storage today? Well, we have data centers in 3 regions around the world with 6 data centers. So we have data stored in the US, Asia, and Europe. And we have thousands of customers using this data. And they're using it because they get anywhere, anytime access to that data that's stored in the cloud, as well as some additional durability and scalability functionality we provide, which I'll be talking about in the internal section in this talk today. Now, in production, we have 70 petabytes of raw storage right now. This storage will be completely used by the end of this calendar year. And based upon our existing customers, we're going to grow this to 200 petabytes by the start of 2012 and continue to grow on from there. So I want to give you just a little flavor of how we're using Windows Azure Storage inside of Microsoft. So one is Xbox. So Xbox is actually sending from their millions of devices from around the world telemetry information into Windows Azure Storage for those that opt into that service. And this basically helps them improve the performance of the Xbox system for their users. And then they'll be releasing a new feature relatively soon, which allows you to actually save your game content up into the cloud. So you can actually play games on one console, then log into another console and continue where you left off. And this is also based on Azure Storage. Another service inside of Microsoft is the Zune Media Service, where they store some of their media content into Azure. And then they serve that media content up through the Windows Azure CDN. And another service is Bing, which has built a near real-time Facebook Twitter search. And I want to double click on this to describe a little bit in more detail how storage is used. So what the Bing group did is they built a service shown here in the yellow box with the VMs. And this is just a hosted service, as Mark described earlier in the prior talk, running on the Windows Fabric controller. And then what they wanted to do is, within 15 seconds of you doing a public Facebook post or a Twitter tweet, have that appear on the public Bing search engine. Okay? So what they did is they basically take that fire hose of Facebook posts and Twitter tweets, and they put it into Windows Azure Blobs. And you can think of Windows Azure Blobs as your file storage in the cloud. So they're just constantly sending up these files. And then their service is consuming those blobs, and what they want to do is they want to annotate and index and rank all that content. And what they use that for, they use Azure Tables to store that index and to aggregate that index over time. Okay? Where Azure Tables provide structured storage for your service to use in the cloud. And then they control the overall pipeline for this using Windows Azure Queues. Once they actually have an index for a set of Twitter tweets or Facebook posts, they then put these back into blobs. And then the Bing engine consumes those blobs and folds them into their index, and then they make it searchable within 15 seconds of you actually doing your tweet or post. Okay? So just a few interesting stats here. We've seen the service do up to 4,000 requests per second to Azure Storage. It typically does about 2 to 3 billion transactions a day. And I just want to highlight the power of Azure. It took one dev 2 months to design, build, and release this whole service to production to get this feature out. Okay. So now I want to talk about what's new with Windows Azure Blobs, Tables, and Queues. And we also have a feature called Azure Drives, where you can actually use a network-mounted drive for your application running in the cloud to get access to NTFS APIs. And all your NTFS calls that are flushed will be flushed to our blob store and made durable. I don't have enough time to go over drives in this talk, but there's a lot of documentation online if you're interested. I'll just be focusing on blobs, tables, and queues. In addition, this is an advanced talk, so I'm just going to quickly go through the overview of what blobs, tables, and queues are, and just focus on the new features as well as the storage internals in the last part of the talk. Okay. Now, in order to use storage, you need to create a storage account. You create a storage account in one of our 6 data centers. And this is the primary location where all your data is stored and all your read and write accesses go to. Once you have your storage account, you can actually create blob containers, and you put your blobs into those containers. You can create tables, store your entities in the tables, and create queues and put messages in those. And shown here is the URL for accessing your blobs, tables, and queues for the storage account you just created. Okay. Now for blobs, as I mentioned, blobs, you can think of it as the file store in the cloud. We provide efficient means for uploading and downloading content. We actually provide 2 types of blobs. Block blobs are the type of blobs that are typically used for storing those files, and those can be up to 200 gigabytes in size. And we provide efficient ways to do optimistic concurrency because we provide strong consistency, as well as creating snapshots and actually creating leases for your blobs. Now, the features that we have available for blobs as of today that are blob specific are shown here. It's a very minor improvement, but it's an important improvement for media players as well as certain browsers. We're basically adding these HTML extensions so that these browsers and media players can efficiently continue if they get a broken connection. Previously, these browsers had to actually go and reload the whole blob down. Not good. So we've added these headers in so they can continue where they left off. There's instructions that will be coming out on how to actually turn this on for anonymous GET requests for blobs soon. Then for tables, as I mentioned, provide structured storage in the cloud. These tables can be very big, terabytes in size, store billions of objects, and we provide a flexible schema. So you can think of this as a NoSQL solution for structured storage. And the data model is quite simple in that you create tables, you store your entities in those tables, those entities have properties, and you can query over those entities and properties. And you can program them with .NET classes as well as query them with LINQ. We support a very standard set of operations, add entities, update, delete, query, and we have this ability of doing what's called entity group transactions. This allows you to do atomic transactions across entities as long as they're in the same partition. And there's information online if you want more details about that. The new 2 features we have for tables right now is query projection and upsert. So query projection allows you to just select the properties that you're interested in. Sort of an obvious feature for a structured storage solution, but we got there. And then upsert allows you to basically send a single request to the storage service. And with that single request, you can say, insert this entity if it doesn't exist, or update it if it does exist. And we didn't have that support before either. So just to go through a quick example, here's a customer table, and assume the customer has hundreds of properties. Okay? But what we want to get is a list of all the customers and just how much they have purchased. Okay? So we can create a customer discount class here, and then do a query where we want to query over the customers table, and we're going to say just select those 3 properties, the customer name, phone number, and then the total purchase, then do the query, and then we can actually just get back those 3 properties, which will save a lot of time if you actually have a lot of properties and a lot of records you want to read in. Okay. Then upsert, as I mentioned, upsert allows you to do this single request to the store to say insert if it doesn't exist, update if it exists. So continuing with our customer table, assume we have this other application that wants to either insert this customer if it doesn't exist or update its address and state. So in order to use upsert, what you're going to do is you're going to say attach to with that customer object for that table, but you're not going to specify an e tag. Okay? This tells us that you're going to do an upsert. You then do save changes, and that command is actually sent to our cloud storage system, and we upsert it based upon what's in the table. Now, if you didn't want to actually do a merge, you actually wanted to place the object if it existed, you can actually say replace on update. This has the semantics where if the object didn't exist, it's inserted. If it did exist, it's replaced with this entity we're trying to upload. Okay. So those are the new features we have available for tables that are specific to tables. Then for queues, queues provide a reliable message delivery system for your service to use in the cloud. And it has the semantics where it ensures that every message is processed at least once. And the semantics are as follows. You put a message into the queue. When you get a message, you specify an invisibility time. That makes the message invisible in the queue for that amount of time. The worker who did the dequeue has that amount of time to basically delete it. And if they don't delete it within that time and the worker crashes, the message becomes visible for another worker to consume. Now I'll go through a quick example of that in 2 slides. Now the features that we have available now for queues are we now support larger messages. So before we supported 8 KB messages, now we support 64 KB. We now allow you to actually treat this invisibility timeout as a lease. So you can keep on extending this invisibility time for your worker and just treat it as a lease. We also allow you to update the contents of the message if you're working on it. And this allows you to store progress information into the message. So if the worker crashes, the other worker can continue where you left off. Then we also allow you to actually schedule future work. So when you do a put, you can actually specify that invisibility time. So you can say, put this message in the queue, but don't make it visible for 2 more hours. So that message is sitting in the queue. Nobody's going to see it. And then as 2 hours go by, it'll appear, and then somebody can process it and do the work. So just go through an example of the middle 2 features with the queue here. You have web roles that are producing these messages into the queue. Then this worker role, let's say it gets the first message, and it sets the invisibility timeout to 5 minutes. And you can see the current time is 7 o'clock, and now the invisibility timeout for that message is 7:05. It's still in the queue, but nobody can see it. So let's progress to 7:04, and the worker is still working on this message. So it's going to extend the invisibility time, basically treating it as a lease, by another 5 minutes. So it sets it to 7:09. And then the worker can also store progress into that message, because it can update the contents of the message. Let's say the time now progresses to 7:07, and the worker role crashes, or that process crashes. Now nobody's processing this message. Well, when 7:09 rolls around, that message will become visible again, and this other worker role can then dequeue the message and continue based upon the progress that's stored there where the other worker left off. Okay, so those new features, I think, actually really round out and make queue much more useful than what we had before. Yeah. Now I want to talk about a feature we just released last month called Storage Analytics. And this is also another feature that we should have had earlier, but we finally got around and got this out. And it allows you to basically really look at what's going on for all of your requests to the storage service. Okay? And we provide 2 things, logs and metrics. Logs provide a trace of all the executed transactions to your storage account. And metrics provide a per-hour aggregate of key metrics that are for the transactions that are occurring to your storage account. And I'll go through both of these in a little bit of detail. So for logs, it lets you answer a lot of questions. Like, how long did this request take? What was the client IP that actually issued a delete container request? We used to get that question sometimes. How many requests are accessing a specific blob, a specific container, or set of blobs? And how many requests is a specific client doing? So these are tons of things you can find out by just doing data mining over those traces. Now these logs are stored into Windows Azure blobs. And the blobs are text files with 1 log entry per line. And each blob contains 1 to many records. And the goal here is that 15 minutes from when your request finishes execution at our blob service, we try to have it appear in a blob log. Okay? And we allow you to configure the logging levels separately for blobs, tables, and queues. You can turn it on for just blobs or just tables. And you can also specify whether you want to log just read requests, write requests, or delete requests, or any combination. Now, one note that this is best effort logging. And by that, I mean we buffer the logs in our front ends for a couple minutes before we actually flush them to the logging system. So if for some reason our front end crashes, we will lose a few records. Shown here is the list of all the fields that we provide for logging. This is online already right now. I won't go through the full list, but I'll just take a snippet of a log record to actually just highlight a few things. So this is just an example of one log record where we see that we're doing a put blob request. We can see that the request was a success with the status code. We know exactly how long the request took. Now I'll go through both what these two mean in a couple slides. We also know what client IP the request came from. And you also notice a thing called the client request ID. What this means is this is a string that you define with your application and pass in with your request. And we just started supporting this about a month ago. So you can pass in with each request this string, and we will put it into the log record. And it's great for actually doing end-to-end tracing from your transactions to the log records. So you can put that same IT into your application logs. And so if you actually want to find what that transaction did from your application logs, you can look up the exact log record and do the match. So I encourage you to definitely use that. And then shown here is an example of what a log record looks like. It's just the data fields with a semicolon separated. Now, moving on to metrics. Metrics provide this hourly aggregate of key metrics for storage transactions to your storage account. So it answers a lot of questions that you might want to quickly find out, which is how many transactions is my storage account executing over a given period of time? How many anonymous blob requests actually were issued against my storage account? And what's going on in terms of the average latency or the availability for my storage account? And there's lots of additional things that are provided. Now, for the transaction metrics, these are provided at a 1 hour time interval. So for every hour of the day, we output a bunch of metrics, which are shown here, such as total transactions, execute against your tables, blobs, queues, the availability, percent successful, network errors, timeout errors, throttled errors, the average latency, ingress, and egress. Then it's provided at a few different levels of granularity. We actually provide a hourly metric showing the summary of everything that's going on for your blob transactions, your table transactions and queues. We also provide these metrics for every single REST API we have. So you can actually look at all the get blob requests to your storage account and see these metrics. Every get blob, every put blob, delete message, insert entity, every single REST API, we provide these metrics. Okay. Now, for blobs, we also provide a few additional metrics. And these are provided once a day, which is what's the current capacity of all your blobs in your storage account and the number of objects. We do plan to provide something like this for tables and maybe queues, and we're currently figuring out when that would be available. So I just want to go through and spend a couple minutes on this concept of the average end-to-end latency as well as the storage latency. Okay? We've had a couple of scenarios where customers have an application, it's running along just fine, then all of a sudden the storage, access to storage is just slow. And they're going, what's going on? Okay? So let me define what these two things mean. So when a request comes into the storage service, we break the timing of that request into 3 parts. The first part is how long does it take to actually receive all the input for the request? The second part is how long does it take for us to actually process the request on a storage service? And the last part is how long does it take for the application to retrieve all the results? And then the storage server latency is shown is the component we measure in the middle. So this is the time it takes for us to, once we got all the input, we process the request and we produce the results. Whereas the application latency includes the time to transfer the results in, as well as to receive the results out, basically to get the results out. So for a couple customers who have had this, we looked at their metrics. And with the metrics, since it's provided at this hourly granularity, it's a very quick query to just get this in a couple seconds. So they did a query to look at for the past n hours, okay, what's my average latency for this application end-to-end latency I just mentioned, as well as the storage server latency, where on the y-axis, we have the average table latency in milliseconds. And as you can see things were going along pretty well, but then when they got to this point, the latency just shot up. But as you can see, the server-side latencies stayed relatively good. So that typically would mean that, OK, there's something going on with the application. Either the application or the VM is overloaded, or maybe there's a network issue between the application and the storage service. So the next thing they look at usually is, OK, let's look at the metrics again, but let's look at the total transaction count to see if the load went up. And lo and behold, it did. So here we have, at this point in time, the load in terms of requests that their application is generating against the storage system went up about double. Okay? But as you can see from the top, with the yellow or gold line there, the server latency is just fine. So still, there's something going on with the application. So then they looked at their application logs and their application performance counters, and they saw that they had high CPU utilization, high memory usage, as well as their VM was actually doing a lot of GC cycles. And the reason why there was such a difference between that application end-to-end latency and the server latency was we were producing the results very quick, but it was taking the application a long time to get the results back because their threads were just thrashing. Okay? And so what they did to resolve their issue was they increased the number of VMs, and they also moved to a larger size VM, which allowed them to use server GC. By default, if you use like a small VM, you get workstation GC, but if you go to a larger VM, you can actually turn on server GC. Okay. So to summarize the analytics, as I mentioned, the logs are stored into blobs. The metrics are stored into Windows Azure tables. And when actually monitoring and generating these statistics and logs for your storage account, we store them in a special logs container as well as metrics tables. So they're actually stored associated with that storage account that's being monitored. And I want to make it clear that we treat these namespaces separate, meaning we have a separate resource limits in terms of capacity as well as throttling for the logs and metrics, because we want to make sure that these stay out of the way of your normal application's usage of your user data. And there's details online for what those limits are. Another question we get is, so what's the cost of using analytics? Well, the cost is the capacity to store the logs and the metrics. And we generate the transactions for storing those blobs, as well as putting the entities into the metrics table. So there's a transaction cost for that, as well as any data mining you do over the data. But we also provide a retention policy where you can set that keep my logs for, let's say, 90 days. Keep my metrics for 180 days. And if you set that, then we will actually delete your logs and metrics when they get that old. Okay? And if we delete the data using our retention policy, then there's no transaction cost for those deletes. Okay. So now I want to talk about geo-replication, which was announced earlier today at the keynote. We have actively turned on geo-replication, and we're excited that we're providing this now for your Azure tables and blobs. And we are providing this so that we have additional data durability for your data in case of a major data center disaster. We only geo-replicate data within regions, as shown here. So only geo-replicate data within Asia, within Europe, and within the US. And when you create your storage account, you choose the primary location where you want to host your data. So for example, if you choose US North, that's the primary location where your data is stored, and all your requests go to US North. But in the background, we asynchronously geo-replicate your data to South Central. Okay? And as I mentioned, the geo-replication is asynchronous, so it stays off the critical path of your transaction. Your data is committed, for example, in US North, success was returned, and then in the background, we do the geo-replication. Also pleased to announce that this geo-replication is at no additional cost. So it's provided with the current price of storing. And if you want to, you could actually turn geo-replication off, though there's no price discount for turning geo-replication off. And if those who actually want to, you can call product support to do that. But just note one thing. When you turn geo-replication off, we're basically deleting the data from the other data center. So if you want to turn it back on, there is a cost to rebootstrap your data, your storage accounts, before it goes to what we call live georeplication. And once it is in live, there's no additional cost. But if you turn it off, turn it on, turn it off, turn it on, then this bootstrap cost would be charged, bandwidth. Okay, so let me give you an idea of geo failover, what that would look like. So you have your storage account here and for accessing blobs. And we registered this with DNS to point to the data center that's the primary location for your storage account. So in this example, again, it's US North. So all your requests are going to US North. Then if there was a major data center disaster, well, we first are georeplicating your data to US South. But if there was a major data center disaster, we first contact the customers affected. And then we would do a failover, and we would basically update that DNS to point to US South Central. And once we do that, this domain name, account.blob.corewindows.net, would now point over here to US South, and then the transactions for your storage accounts would start working again. So there's a few key points here. One is the existing URLs that you have will continue to work once we update the DNS. But we will only trigger a failover if we have to, absolutely have to. I mean, we're going to do whatever we can to get your data back durable in the primary location. And the reason for that is the georeplication is asynchronous. If we do the failover, there could potentially be loss of recent updates. So we'll do what we can to definitely make sure we get the data back up in the primary. And the failover is only used if there's a major disaster for a data center. Now, a common question that we'll be getting today is, OK, how long does it take to actually georeplicate the data? It typically takes within a few minutes to georeplicate the data. But at this time, for this first release, we don't have any SLA guarantee, but it is typically georeplicated within a few minutes. Okay. So now I want to move on and talk about Windows Azure internals. And what I want to try to explain here is some of the internal architecture that we have so you can better understand how we keep your data available, durable, and scalable. I'm only going to be able to talk about some of the architecture at a high level and dive into a couple areas, but there's a paper coming out in SOSP next month with all the details in there. So definitely check out the paper if you want the details of everything we're doing. OK, so I want to start off talking about the concept of a storage stamp. Now, a storage stamp is basically a Windows Azure tenant. Mark talked about this in the prior talk. So it's just a tenant like any other tenant, pretty much, running on the Windows Azure Fabric controller. We rely on the Fabric controller to manage our upgrades and keep our roles running, et cetera. So this tenant consists of 10 to 20 racks of storage. And running the storage roles that are shown here. And then when you create a storage account, your storage account is actually assigned to a specific stamp. And all the data for your storage account is stored within that stamp, stored within that 10 to 20 racks of storage. Then to scale out additional capacity, this 10 to 20 racks of storage represent around, depending upon our generation of our SKU, 2 to 30 petabytes of storage. So to get additional capacity in a data center, we just stamp these out. That's why we call them stamps. So we create another tenant, a storage tenant. Then we have what's called a storage location service that manages all the storage tenants around the world. And what this is in charge of is account allocation to those storage stamps, as well as account migration, account load balancing. It's also in charge of setting up georeplication for accounts. And it's also in charge of doing the failover if we need to trigger a failover for a certain set of accounts. Okay. So now what I want to do is I want to dive into some of the details of what goes on within a storage stamp. So I'm going to talk about the 3 levels, starting with the lowest layer, the DFS layer. So the lowest layer here, you can think of this as a distributed file system. This provides an interface for the upper layer, the partition layer, to store its files into. And it's responsible of making those files durable. We call these files extents. Okay? So the DFS layer takes these extents that the partition layer wants to write, and then it replicates them 3 times. We also checksum all data, and we validate that checksum on every single read of your data, as well as we scrub all of your data about every 3 days. And then if there's a failure of a node, disk, rack, or if we get a checksum mismatch, we'll take one of the healthy replicas and re-replicate that to get you back up to a healthy number of replicas for your data. Now, one thing I want to touch on briefly, which I don't have a lot of time to go in, is the load balancing done at this layer. There's a few things we do. As I mentioned, when you actually create a new extent, we replicate it 3 times. And we do a random allocation of those 3 extent replicas across a candidate set of machines that have available resources in the stamp. And we make sure to place those 3 replicas across different fault domains and upgrade domains. And I think Mark probably talked about fault domains and upgrade domains in the prior talk. Basically, by placing those across those different domains, if a rack goes down, you still have 2 copies to read your data from and to re-replicate the data from. And the same thing if an upgrade domain, if we're upgrading a set of servers, you still have 2 copies to which to read your data from. Okay. Now, we also do what's called a read load balancing. With our system in the DFS layer, each of the replicas can be read from. So you don't have to go to a specific replica for reading. And then we do read balancing to try to balance out and not have any too hot servers based upon the read load. Then for the write load, we do this technique called journaling, where every server has a journal drive, and we journal the writes to try to keep them at a low latency. Then we asynchronously put them to the data disk that they belong in. There's good details about these techniques in the upcoming SOP paper, so definitely check that out if you're interested. Now, for the partition layer, this is the layer that actually understands what an object is. It understands what a blob is, an entity is, a message is. And so it's in charge of actually providing strong consistency for those objects, as well as optimistic concurrency. Okay? It takes these objects and then it stores them into these extents that the DFS layer then manages. So it leaves all the durability of placing this data on disk to the DFS layer. But it does have a play in a form of replication in that it is in charge of actually doing the georeplication. We also call it interstamp replication. So the partition layer, once it actually commits an update to the DFS layer, it will queue up to send this log via log shipping to the other data center to georeplicate that transaction over there. The partition layer over there will then commit that, replay that log entry, and then make it durable in its DFS layer. Okay? So for georeplication, we keep your data durable in those 2 data centers, in those 2 stamps, by the DFS layer. So we have several copies of your data in both stamps. Now, one of the key challenges for the partition layer is providing this massively scalable object index. And I'm going to get to more details into that in a couple slides. Then the front-end layer, this is just a set of stateless servers. And it's in charge of several things like authentication, authorization of requests. It also deals things like logging, QoS, throttling. And it also does request routing. So you can have a request that comes in, a write request. It knows where to route, what partition server to route this request to via what we call a partition map. And I'll get into that in a few slides. It gets routed to the correct partition server, serving those objects. The partition server then makes it durable in the DFS layer, and then the result gets sent back out. So let me now dive into the partition layer and then talk about this scalable object index and what it has to do. So the challenge that the partition layer has is inside this storage stamp, there's potentially hundreds of billions of blobs, entities, messages across all storage accounts. Okay? So it needs a way to efficiently enumerate them, get them, query them, update them. And it has to deal with the fact that the traffic patterns are unknown. One customer's traffic pattern looks very different from another customer's traffic pattern. So it has to deal with these hot objects, peaks, traffic bursts, etc. across this massive index. So we need a scalable index that we can actually spread across hundreds of servers and then dynamically load balance where we want to be able to move parts of the index across our servers and say this server you're responsible for this part of the index. This server, you're responsible for this part of the index. We want to be able to load that, balance that around within seconds if we have to. And so what we did internally inside of our object layer is we provide what we call object index tables. Okay? So we have a blob index, an entity index, and a message index. And this is an index of all the blob objects across all storage accounts in that storage stamp, an index across all entities, and across all messages. And then the partition layer, what it does is it monitors dynamically this index. And it finds hotspots that are starting to form, and it load balances this index across the servers and spreads it around. So it basically dynamically looks at what load is going to what part of the index, and then moves it around to different partition servers. So let's just go through an example of sort of what this looks like for the blob index table. So here we have this massive blob index table. It contains the index of all the blobs for all customers in the storage stamp. Okay? And we have in the storage stamp, just as an example, 3 partition servers and a partition master. And what we're going to do is, based upon the load for this example, we're going to split it into 3 partitions. We call these index range partitions. And note that we can actually split a container index across multiple range partitions. So we can actually take a container and then spread its index over hundreds of servers if we need to. Okay? These index partitions, or range partitions, are assigned to partition servers by the partition master. And then the partition master maintains what we call a partition map. And this is a map of which partition servers are serving which part of the index. Then the front ends cache this partition map. So if it gets a request, for example, to storage account Andrew, it can look that up and know, well, I need to forward this request to partition server 1, forwards the request, partition server 1 processes it, and then it's on its way. Okay? Now, one important point here is that each part of the index is only served by one partition server at a time. And that partition server that's serving that part of the index is responsible for providing strong consistency over the objects in that index and performing all the operations that you could do for your objects, such as enumeration, get, put, etc. Okay, so this sort of explains how we split the index up. Let me spend a slide just talking about how we do the load balancing, just to finish that up. Okay, so here we have our 3 layers. We have our set of front ends, partition servers, and our DFS layer. And in the example, we've already taken that blob index, and we have broken it up into several range partitions. And the partition master has assigned that to a bunch of partition servers. Also shown in the graph, in the slide, is a load bar. Everything's green now. Everything's going along just fine. We're processing all requests as they come in as fast as possible. Let's say we have some requests that come in for the green partition, meaning that these requests are trying to access this part of the index represented by that green partition. So each partition, remember, is just part of the blob index. So it looks up in the partition map what server is serving the green partition, and it says, partition map says server 3, and so the request is forwarded there in process. Let's assume that we also have load come into this front end that says, I want range partition that's yellow. Okay? Well, it looks at the partition map. Partition server 3 is where it's at, so it forwards the request there. But now the load's getting high on this server. And the partition master is just kicking back, watching all this go on, and says, OK, I need to reduce the load on partition server 3. It can do 2 things. One is it could actually take one of the existing partitions there and split it, like I showed in the prior slide, and then load balance that away. Or it could just take one of the existing partitions and say, OK, partition server 3, stop serving that index range. Partition server 2, you serve that index range. And that's what it does in this example. So it talks to partition 3, says, hey, stop serving that index range. Partition server 2, you serve that index range. Then updates the partition map. And then the front end starts directing the request to partition server 2. And then, as you can see, the load balances itself out. And that's what we spent a lot of time building in the partition layer. So we have this automatic load balancing of this massive index range. Now, a few key points here is that the load balancing is triggered on hot partition ranges or partition servers. And as I mentioned, the two things we can do is split out the range index into smaller ranges and spread that out, or just load balance the existing ranges that are currently there. And probably the most important point here is that no data is actually moved on disk. The data is stored in the DFS layer. So all we're doing is saying, partition server 3, stop serving this index range. Partition server 2, you start serving that index range. Then partition server 2 can then go to the DFS layer and basically get the metadata for the index and start serving it. There's basically no data moves around on disk. We only are changing the index assignment across the servers. Okay. So now I want to pop up a level and talk about the data abstractions and what do you need to know in order to actually use Windows Azure storage to get the most out of our data abstractions in terms of scalability. Okay? So to understand what to do for scalability, there's sort of two things you need to look at. One is, what's the scalability of a single storage account? And what's the scalability of all the objects that we actually would store into that account? So for a single storage account, the current scalability targets we have right now are a single storage account can store up to 100 terabytes of data. It can do up to 5,000 entities per second, or transactions per second, and process up to 3 gigabits per second. If you need to use more storage than that, so you use more storage accounts. Our large customers who are storing petabytes of data, they use many storage accounts, and they typically use many storage accounts across the world, across our data centers around the world. And then they build at their application layer some partitioning logic to partition their users or data across those storage accounts. Now, over time, we do expect to increase these limits. We have these limits right now because, as I mentioned, a storage account is completely stored within a single storage stamp. And we have various sizes of storage stamps that range from 2 petabytes in size to 30 petabytes in size. Then within an account, it's very important to know what is the scalability of the data structures we have for blobs, tables, and queues. And this is related to the indexing I showed earlier. So we can actually partition that blob index that I showed down to a single blob, to where we can actually have a given server just serve a single blob. And the scalable throughputs that you can actually get for a single blob is up to 60 megabytes per second. We can also adjust that index for the table index, that massive one that I talked about, down to the partition key level that you specify for your application. So when you use tables, every single entity you have has an application-defined partition key. And we can partition that index at that partition key. So for a single partition key in a table, you can do up to 500 entities per second. The table itself can do up to 5,000 transactions per second, which is the account limit. But a single partition in the table can do up to 500 entities per second, which is basically the throughput that we restrict a single partition to do on a single server. Then for queues, the partition key for queues is actually the queue name. This means all the messages that are actually stored in a queue are actually handled by a given partition server. So the current throughput that we have for a single queue right now is 500 messages per second. Okay. So in summary, I hope you come away with the talk today with a high-level understanding of the new features that we provide. We'll be posting on our blog by Friday, I believe, how to actually use these new features with more details. And if you want more details about the internals of Azure Storage, definitely check out the paper that's coming out next month in SOSP. Okay, and I'll take some questions. And don't forget to fill out your feedback forms. Oh, there you go. I can't hear. Mic on? We go here for a moment. Can somebody turn the mics on? Any? Oh. You can come up closer and talk. Well, if the mics are working, I guess let's end the talk now. And I'll stay up here for as long as needed to answer questions. Thanks for coming.